In today's podcast, we are going to be looking at finding measures of angles formed by secants, chords, and tangents in circles, and review finding measures of all the angles in a circle. First off, when you look at angles formed by secants and or chords, notice it could be either because chords are just parts of secants. If I had extended the lines beyond the edge of the circle, you could have seen them as secants. Now, look at the arcs that are inside the angles. For example, let's just take a look at the arc that is inside this one angle near the middle of the circle. You can see where I've drawn it. As I move the secant, what happens to arc AB? Notice where B is on the circle. It would be moving further. In other words, B would now be down here and D would be now down here. Now notice when I started, arc AB was a short arc and arc CD was the longer arc. Now as I move down here, arc BD AB becomes the longer arc and arc CD becomes a shorter arc, but the angles have not changed. This leads us to our first theorem. Because the angles are vertical angles and they don't change, these are the same measures, but the arcs inside them are different measures. The key to this is that you just basically have to average the arcs in order to find the measure of the angle. So in this example, this was angle 1, this was angle 2, this was angle 3. If I want to find the measure of angle 1, the first thing I need to do is average the arcs that are intercepted on angle 1 and on its vertical angle. So I'm going to average arc AB and arc CD. So I'm going to take 36 plus 140. I'm going to average that, which means I'm going to divide it by 2, and I end up with 176 divided by 2, which is 88 degrees. So if angle 1 is 88 degrees, I know its vertical angle is also 88 degrees because vertical angles are congruent. And then I could find the remaining angles because these angles are linear pairs. And we remember that linear pairs are supplementary or add to 180. So angle 3 would be 92 degrees and angle 2 would also be 92 degrees. This leads us to our first theorem. And our first theorem says, if an angle is formed by two secants or chords, the measure of the angle is half the sum of the arcs intercepted by the angle and its vertical angle. Again, basically all this is doing is averaging, and I'm just going to call them, it really isn't the name of them, but I'm just going to call them the vertical arcs. It's the arcs that are intercepted by those vertical angles. Now we're going to look at another example. In this case we know the angle, but we're looking for the measure of one of the arcs. So what I know is that 50 degrees equals half of x degrees plus 35 degrees. Now the easy way to do this is to go ahead and multiply both sides of our equation by 2 to start with, because that will eliminate our fraction. So 100 degrees will equal x plus 35 degrees, and our answer is 65 degrees equals x degrees. In all of these cases, the vertex of the angle was inside the circle, but it was not actually at the center. Now let's look at the case where the angle is formed by a secant and a tangent, which means the vertex is going to be actually on the circle. And when the vertex is on the circle, all you have to do is take 1/2 the measure of the intercepted arc. This is exactly like it was for the inscribed angles. In fact, whenever the vertex is on the circle, the measure of the angle is always 1/2 of the intercepted arc. Our intercepted arc here was 250 degrees, so the measure of angle 1 is going to equal 1/2 of 250 degrees, or 125 degrees. We have one more situation that's actually broken down into 3 cases, and that's when the angle is formed either by two secants, two tangents, or a secant and a tangent. And these are all when the vertex is located outside the circle. Notice our examples. This is two secants. This is two tangents. This is a secant and a tangent. Now, on each of these, instead of adding the arcs together and dividing by 2, we subtract the arcs together. Now notice on this, again, we have a large arc and a small arc. The larger arc is always going to be farther away from the angle. So in this case, my large arc is going to be yellow. So this would be my large arc in the first case. This would be my large arc in the second case. And this would be my larger arc in the third case. And my small arc, I'm going to make purple. So it's the little arc here, the little arc here, and the little piece of the arc right in there. And why that went to a straight line, I'm really not sure. Now let's take a look at the example. We're following the formula that the angle equals half of the arcs subtracted. So in this case, we know the angle is 62 degrees. So 62 degrees is going to equal 1/2 of, and our larger arc is always farther away from the angle, so it's 141 degrees, minus our shorter arc, or smaller arc, which was x degrees. Now, in this case, again, it's easier to get rid of the fraction first, so we'll simply multiply both sides by 2, and we end up with 124 equals 141 minus x. So I can add x to both sides and get x plus 124 equals 141, or x equals 17. Since this is an arc, it's 17 degrees. Now let's take a look at the next one. This is the circumstance of a tangent and a secant. Again, it's the same formula. The angle, which in this case was 55 degrees, equals 1/2 of the larger arc, or the farther away arc, which is 6x degrees, minus the closer arc, or smaller arc, which is 40. Again, the simple way to do this is to multiply by 2 to eliminate the fraction, and we end up with 110 degrees equals 6x minus 40, which leads us to 6x equals 150, and x equals 25. So the measure of this arc out here was 150 degrees, but x actually equaled 25. Now let's look at the third case, and the third case is probably the trickiest because they're asking us for x and they did not give us any of the arcs on the circle. And the key to this is to remember that if one part of the circle is x, the other arc of the circle is 360 minus x, because it's everything but the x out of the 360 degrees. So as we set up our problem, we're going to have 50 degrees equals 1/2 of 360 minus x, that's the far arc, and then minus the near arc, which means we're going to be subtracting another x. So what I have is 50, let's multiply by 2. Let's get rid of that fraction. So 100 equals, and let's simplify what's in here now, and what's in that parentheses is 360 minus 2x. So if I subtract 360 on both sides, I get negative 260 equals negative 2x. Dividing by negative 2, I get x equals 130. That means the small arc is 130 degrees, and the large arc is 230 degrees. This is actually all the information you need to know about finding angles in circles, but now let's review it so that you can see the differences and likenesses between them. There are basically 4 types of angles formed in circles. One of the angles is when the vertex is at the center of the circle, and in that case the measure of the angle is going to be equal to the measure of the arc that it intercepts. The second is the vertex on the circle. In that case, the angle equals 1/2 of the arc. The third case is the vertex inside the circle, in which case you average the arcs. And the fourth case is the vertex outside the circle, in which case you subtract the arcs and take 1/2. Now, there's a pretty large problem down here, and your job is to find the measure of each angle. I am going to make a suggestion to you, which is to find all the missing arcs first and then worry about the angles. I would like you to try this problem on your own, and then you can check your work against that on the podcast. Notice because of the diameter, I was able to determine that arc EF was 75 degrees and arc FG was 85 degrees. When I looked at angle 1, the vertex was at the center, so the angle was equal to arc BD. I had to add arc BC and CD together to get 55 degrees. Angle 2, it was going to be half of arc BD because it was on the circle. So half of 55 was 27.5 degrees. Angle 3 I determined because triangle FAD is an isosceles triangle because the radii of the circle are congruent, which meant those two angles were congruent. So it was the same as angle 2, 27.5 degrees. Angle 4 was located inside the circle but not at the center, so I had to average the arcs that it intercepted. So I added BC and FG together and divided by 2 and got 57.5 degrees. Angle 5 was on the circle, so it was half of the intercepted arc, and it intercepted arc CG, so half of arc CG was 62.5 degrees. Angle 6 was located at the center, so I added arc DE and EF together to get 125 degrees. And angle 7 was outside the circle, so I subtracted the two arcs and divided by 2 and got 30 degrees. And angle 8, also outside the circle, subtract the arcs, divide by 2 for 12.5 degrees. This concludes today's podcast.